Welcome back to this week of renewable energy generation. In this video we'll discuss the theoretical potential of wind energy. In week 2, wind energy technology will be discussed in great technical detail. In this lecture we will do a simple back on the envelope calculation. The learning objectives are understand the basic physical principle of wind energy and wind turbines. Calculate and analyze the important performance metrics of an onshore and offshore wind energy farm, the conversion efficiency, the energy yield, the capacity factor, the surface power density, the CO2 emissions, and the energy payback time of a wind turbine in a farm. And to be aware of the pros and the cons of the integration of wind energy into the energy system. This is the image most people will visualize when they think about wind energy. A large wind turbine with slowly rotating blades. The rotation of the blades is caused by the wind. But where does wind come from exactly? Again, let's start with the sun. Solar rays cause an uneven heating of the surface of planet Earth, creating temperature and pressure gradients. The temperature gradient can be the result of a number of factors, such as the position of Earth with respect to the equator, the presence of clouds, the presence of large bodies of water, and even the type of terrain. The temperature gradients induces a pressure gradient, which leads to an airflow from a high pressure to a low pressure area. This is what we experience as wind. The wind carries kinetic energy, which is converted into mechanical energy by means of a wind turbine. Next, a generator converts the mechanical energy into electrical energy. An electronic converter in combination with a transformer links the generator to the grid, ensuring maximum power. The primary energy of the wind is given by the mass of air traveling at a certain speed. This is called the kinetic energy and is characterized by this equation. E kin equals half the product of the wind mass and the velocity of the wind squared. Similarly, the wind power, P wind, is calculated as the kinetic energy per time, which means that the amount of air mass passing a surface A in time is considered. Wind power equals half the product of the mass flow and the velocity squared. The mass flow itself is equal to the product of the air mass density and the volume flow, as the air volume flow is equal to the cross-sectional area of the flowing column multiplied with the velocity of the air. If we consider that the cross-sectional area of the flowing air column is equal to the surface covered by the rotating blades of the wind turbine, which is equal to P times the half blade diameter squared, we can describe the full wind power incident on the wind turbine. The wind power incident on a wind turbine is expressed in watts, the density in kilograms per cubic meter, the area in meters, and the velocity in meters per second. This equation shows that the power is highly dependent on the wind speed. As you can imagine, the height and the surroundings of a wind turbine greatly influences the wind speed. High wind speeds are achieved at large hub heights and in close proximity to the coast. To obtain the power output of a wind turbine, the potential power in the wind needs to be multiplied by the system's efficiencies that include both the conversion efficiency from kinetic energy to the mechanical energy, turning the rotor, and from mechanical energy again to the electrical energy. The maximum theoretical conversion efficiency from the kinetic energy to the mechanical energy, turning the rotor, is called the Betz limit, named after Albert Betz, a German physicist. This limit is independent of the design of a wind turbine in open flow. The law is derived from the principles of conservation of mass and momentum of the airflow through a magic disk, being in this case the rotors, that extracts the energy from the wind flow. Following Batt's law, the amount of energy a wind turbine can be extracted from the airflow cannot be more than 16 to the 27th ratio, or 59.3% of the total kinetic energy in the wind. Commercial wind turbines have their peak efficiency and optical wind speeds at 40 to 50%. The rated power is the maximum power a wind turbine can produce electricity in a safe operation mode. The rated velocity corresponds to the wind speed at which the rated power operation conditions is reached. The threshold wind speed corresponds to the minimum wind speed required for the wind turbine to start rotating and to generate usable energy. Below this speed, the wind can deliver insufficient torque to overcome friction and inertia. The turbine delivers, in that case, zero power. The cutoff velocity corresponds to the maximum wind velocity at which the turbine is allowed to operate. Above this wind velocity, the turbine automatically brakes and shuts down to prevent structural damage from extreme wind loads. This turbine delivers then zero power under these conditions. Between the rated velocity and the cutoff velocity, the turbine uses power control. A constant rated power is maintained using braking or pitching of the blades. The actual energy yield of a wind turbine is determined by the wind conditions the turbine is exposed to during the year. In this plot, an example of a frequency of occurrence of different wind speed ranges is shown. If we project the power curve of the wind turbine over this graph, the frequency of occurrence of the different operation conditions of the turbine can be defined. For example, the periods that the wind speed is below the threshold velocity and above the cutoff velocity, the turbine produces no power. Whereas during the periods that the wind speed is between the rated velocity and below the cutoff velocity, the output of the wind turbine is at the rated power. And during the periods that the wind speed is between the threshold velocity and below the rated velocity, the output of the wind turbine is increasing with the wind speed. The annual energy yield is equal to the average power delivered during the year multiplied by the duration of the year. The average power is given by the summation of all products of the frequency of wind speed occurrence multiplied with the power output at that wind speed, divided by the summation over all the occurrences. The capacity factor is the annual yield divided by rated energy output, which means if the turbine would be operating full time at rated power. This leads to the expression shown here. Typical wind turbines installed onshore have capacity factors of 20 to 40%, whereas turbines offshore have typical capacity factors of 30 to 50%. The capacity factor of offshore wind turbines or wind farms is larger as ocean winds are stronger, more consistent and less turbulent than land, and obstacles like hills or buildings are not around. In addition, offshore wind turbines can be larger and taller than the onshore ones. In addition, the capacity factor are influenced by the maintenance downtime of the wind turbines, but also environmental factors can play a role, like icing on blades can reduce the efficiency or even result in downtime. Let's consider an onshore wind turbine, where the latest wind turbines have a typical size of 7.5 megawatt. Considering a capacity factor of 23 to 44%, a single turbine has an annual yield of 15 to 29 gigawatt hours of electricity per year. Let's consider an onshore wind turbine, where the latest wind turbines have a typical size of 7.5 megawatt. Considering a capacity factor of 23 to 44%, a single turbine has an annual yield of 15 to 29 gigawatt hours of electricity per year. To calculate the aerial power density, we use the minimal spacing distance between the wind turbines required to prevent a wake effect and wind shading effects between the turbines in a wind farm. If we assume that this minimum spacing is equal to 5 times the diameter of the rotor, the typical power density of this onshore wind turbine would be around 2 to 4 watt per square meters. Note that a large part of the area can still be used for other purposes, allowing land below wind turbines to be used for agriculture or grazing, to mention a few. Offshore wind turbines can be larger and taller than the onshore ones. Let's consider an offshore wind turbine where the latest wind turbines have sizes of around 15 megawatt. Considering a capacity factor of 30 to 50%, a single turbine has an annual yield of 39 to 66 gigawatts of electricity per year, while the typical aerial power density increases to 3 to 5 watts per square meters in reference to the onshore wind farms. What about the carbon footprint at the total life cycle greenhouse gas emission per unit of electricity generated? The carbon footprint for onshore wind energy is 7 to 11 grams of CO2 equivalent per kilowatt hours generated, whereas it is 8 to 14 grams of CO2 equivalent per kilowatt hour generated for offshore. These low carbon footprints are a factor 120 to 35 smaller in reference to generating electricity with fossil fuels. The energy payback time is the duration that a renewable energy system must operate to generate the same amount of energy that was consumed during its cycle, including manufacturing, installation, operation and disposal. For wind energy, the typical energy payback time is 4 up to 11.5 months. The energy return on the energy investment is the ratio of usable energy delivered during the lifetime of the generation system divided by the energy consumed by the generation system during its life cycle. If we consider a lifetime for a wind turbine of 20 to 25 years, the energy return of energy investment can vary from 20 up to 60. Among the advantages for the wind energy are the technology's cost effectiveness, providing inexpensive electricity over the lifetime of the turbines. Once installed, wind turbines have low operational and maintenance cost. Another advantage is its low carbon footprint. Wind energy technology is the low-hanging fruit in climate change mitigation. It can significantly reduce the CO2 emissions on the short term. This domestic energy source improves the energy security as well, as the region where wind turbines are installed relies less on the import of fossil fuels. On the other hand, challenges are the intermittency of wind energy. The wind does not blow all the time. And the initial investment, like any renewable energy technology, is high. While operational costs are low, the initial construction and setup costs are high. The best wind resources are often in remote areas, posing extra investment on the transmission lines. Turbines can pose risks to wildlife like birds, and they can create noise pollution, and the aesthetical perception of wind turbines by locals can hinder or delay the acceptance of this renewable technology in society as well. Let's put these numbers in reference to the world primary power demand in 2024, being 19 terawatt. With this map, we can visualize what the surface area is required to cover this demand with the technology discussed in each video. And if we consider the total area needed in the form of wind farms, and assuming a typical surface power value of 2 watts per square meters, we would need to cover 9.5 million square kilometers with wind farms. This would be around 1.8% of the total surface of planet Earth and or 6.2% of all land area of planet Earth. So we have discussed the important performance metrics of the hydroelectricity plant: conversion efficiency, energy yield, capacity factor, aerial power density, the carbon footprint, and the energy payback time. Wind energy is a renewable electricity generation technology that has a low cost and low carbon footprint. In the next video, we will discuss another renewable energy source: solar energy. So see you back in the next video.